Okay, YouTube, in this video we're going to start to explore the concept of a limit, which limit, you've heard this before probably in a calculus context, but it's kind of the fundamental idea behind all of calculus. And so we're going to look at a specific problem here and kind of talk about how limit might be associated with this, but maximizing area is going to be our goal here. And so let's say we're given 24 inches of wire, and so we have this wire right here that is 24 inches in length. And what we seek to do is to form a rectangle whose area is as large as possible. So the real question here is, what are the dimensions of the rectangle that are going to produce this maximum area? And so to start, let's do this. We say let W represent the width of the rectangle, and we'll let L represent the length of the rectangle. What I want to do is write an equation that represents the perimeter of our rectangle. So what we have is this length of wire here with which we are making a rectangle. So let's go ahead and sketch our rectangle here, and I kind of conceptualize this as having the length be the longer side, and we'll call this the width here. But with respect to perimeter, we could start by just saying that our perimeter here would be the sum of all the sides. And so because we have two lengths and two widths, we'll say 2 widths plus 2 lengths here is going to be our perimeter. Now the fascinating thing about this is that we are certainly wrapping this piece of wire around this rectangular space. And so if that's the case, then we actually already know the perimeter of this, and we could say that 24 is our perimeter, and that's equal to 2W's plus 2L. So I'm going to put a box around this. And this is going to be our equation that represents our rectangular perimeter here. Now, letter B says using the fact that the area of the rectangle is given as the length times the width, what we're going to do is use the equation that we just formed here in part A to rewrite the area formula in terms of the width only. And so our goal is this. We're going to be taking our area formula, and what I'd like to do is write area as a function of just the width, which means we need to get rid of this L right here. But the way we're going to do this is we're going to take our perimeter formula here, which is this 24 inches of wire here, which is 2W's plus 2L's. And what we'll do is we'll solve for L. So solve for L, then substitute. Okay, and we're going to substitute this into our area formula. That way our area formula is all in terms of the width. And so solving for L here, I suppose we would subtract 2W from both sides, and so we end up with this 24 minus 2W equaling 2L. But of course here we'd follow up by going ahead and dividing by 2. So I'm going to write a little expression here. We say the length is 24 divided by 2, which is 12, minus 2W divided by 2, which is W. We get this idea that the length then is always 12 minus the width. So with our area formula over here now, what we could do is we could actually say that our area formula is equal to the length times the width, where what we're going to do is we're going to substitute in this expression right here. So we get 12 minus W times W, or in other words, what we could do is we could write our area function. So we're going to write area function as a function of the width, and we would say that this area function really is area as a function of width is equal to, and I'm going to go ahead and distribute this here, we say a negative W squared plus 12W. This is our area function of our rectangle here as long as we know the width. And so what I want to do here for part C is essentially this. I want to fill out the following table. In this table, what we're going to see here is it represents the rectangle's area as a function of its width. And so we could find the area right here as long as we know the width. So in our table, you're going to see this here, that I've got several different width values for our rectangular space and then the resulting area. And so in order to get this resulting area here, what we're going to do is we're actually going to plug these values into our area function. So to make this a little bit easier, what we're going to do is we're going to use a graphing utility, which I guess I mean to say is we're going to go up to y equals, and we're going to put this in for our function here, except for using y's and x's. I suppose we would have y equals negative x squared, okay, plus 12 times x. So if we take a look at this here and we go and I suppose make a table of values, I'm going to scroll down on my table a little bit here, but we can see that with a width of 3, we would have an area of 27 square units. With a width of 4, we would have an area of 32 square units. So I'm going to fill these in here. We get 27. I suppose we looked at this and we said that was a 32. So 32. We'll hop over here to, how about 6, 8, and 9? I've got some whole number values here. At least at 6, we say 36. Okay. For 8 here, I'm going to go back and we'll scroll down to where we get a width of 8 here. 8 is 32 and 9 is 27. So we get back to 32 and we have 27 here. And certainly we could plug in 5.5 into this function here. What I'm going to do is I'm actually going to go back to my table set and I'll just ask my table to go by halves. And so when I go back to my table now, I could certainly see that 5.5 would be 35.75, so 35.75. And for 6.5 here also, we get 35.75. So that is to say that we're seeing something happen here. In terms of area, we wanted the maximum area. we can see that the maximum area is going to occur if this thing has a width of 6. And so to look at this contextually, we say if this was 6, well then this would be 6, but if the perimeter all added up to be 24, well then the length would have to be 6 also, and this would also have to be another length of 6. In other words, this would have to be a square. So in order to make a maximum area, this is definitely going to need to be shaped like a square, and the smaller or bigger the width gets, the longer the length gets, then we start to get something that looks more like this, that takes up less area than this right here. So with respect to what we can conclude here, we can see that as the width, and I suppose we saw the maximum area occurs when the width is 6 here, but as the width gets closer and closer to 6, and that's coming from lower values than 6 and from upper values of 6, what we can see is that our function value, our area function here, they both started to approach a single value of 36. And so what I'd like to do is kind of answer our question first of all. We'd say the width must be 6. So the width must be 6 in length. So 6 inches of length, or 6 in length. But in terms of conclusion, what I want to do now is introduce the concept of what we call a limit. So in limit notation, what we just did here was we said that we had the area of a rectangle as a function of its width here. And so here was our area function. But what we see is if we were to write the limit of this function, okay, we would write it as LIM. As the width approaches 6 of our area function, what we see is that the area is approaching 36. So we're going to pick this expression apart quite a bit. But really when we talk about limit, okay, what is limit here? What we're doing is we're asking or answering a question here. We're saying, what is the value that our function is getting, and I'll write really close to, as the value of the width is approaching 6. And so I noticed something here. I'm going to go back over and write on my limit here. This right here shouldn't be W-6. I don't know why I didn't write an arrow here. But what we see here is this. We're saying that what is the area really getting close to here as our width value gets really close to 6. And clearly in the table up here we're saying is the width is getting really close to 6, then our function is getting really, really close to 36. So this right here, this is what we're going to call a capital L, and it's just a number, but we refer to this as the limit because it is the value that our function is getting really close to as our, say, input, or in this case, width gets really close to another value. So in the next video, we'll look at this in a more, I guess, formal definition. Cheers.